All right, students, welcome to your Beers Law and Spectrophotometry and kind of dilutions and solutions AP problem walkthrough. I'm going to spend the first couple minutes going through a couple conceptual questions, one of which will actually be addressing solution and polarity and solubility, and then we'll go through a beer law walkthrough and then one, I believe, short FRQ completely. So go ahead and start with me on page 8 of the 2023 year workbook. And we have question 31. A student investigates various dyes using paper chromatography. This was introduced, by the way, this method of separation of solutions and mixtures was introduced in unit 1. And it totally is based off of the principle of likes dissolve likes. Oops, likes dissolve likes. So what we have here is what we do is we put on a small sheet of silica paper. We put various samples of either reactants that we think are in a solution, and then of course the unknown sample that we're trying to figure out, and we put it into a solvent of some sort that either has polar or non-polar characteristics, and we see how fast and how far the dotted samples travel up with respect to the solvent that it's in. And we know that the more a sample will travel with the solvent, the more similar in polarity that sample is. So what we have is the student has samples of 3 pure dyes labeled A, B, and C, and an unknown sample that contains one of the 3 dyes. Okay. The student prepares the chromatography chamber shown above on the left. I think I'm definitely meant on the right. Sometimes we change the formatting, so either way, it's shown. Okay, shown by putting a drop of each dye at the indicated position on the chromatography paper, a polar material. So the paper is polar. That's important to kind of just make a mental note of. And standing the paper in non-polar solvent. Okay. So the developed chromatograms are shown above or are shown. I'm just gonna leave as shown because sometimes we reformat this. Which dye, A, B, or C, is the least polar? Justify your answer in terms of the interactions between the dyes and the solvent or between the dyes and the paper. So we know that I personally think it's easier to justify between the dyes and the solvent. The dyes and the paper, I just wasn't taught to think from that perspective. So I think it's easier to say what traveled with the solvent, that must be non-polar. So whatever didn't travel with the solvent is polar. So what we say is which dye is the least polar, i.e. another way of putting it is the most non-polar. And that means it's going to travel the most with the solvent. So based off of our data, we would say that dye C is the least polar and most non-polar as it traveled the greatest distance with the non-polar solvent. Okay. B, which dye is present in the unknown sample? So the unknown sample seems to demonstrate, if we were to draw a little sketchy line, seems to demonstrate a middle ground between dye A and dye B traveling. So what you could say is either, you could choose. I'm personally going to say dye B, the unknown, because I feel like the distance is most similar to dye B. So the unknown dye is likely dye B based on similar, okay, based on similar solvent interaction. Okay, based on similar solvent interaction. I don't even know I'm like Carlos Loves. Hi, sorry, 1 second. Okay, so based on similar solvent interactions, the unknown dye is likely dye B based on similar solvent interaction. Again, applying likes dissolve likes principle, dye di B and the unknown show low solubility with the solvent. And are likely more polar. Okay, so that's kind of the walkthrough. I know it's a bit more of a review on solubility in general, but let's go ahead and move on to Beer's law, the new stuff that we talked about. So remember, Beer's law is a way of using dilutions and molarity and solubility to identify and predict the concentration of an unknown sample. So here on, we have question 36, the student measures the absorbance of the 0.08 molar, 0.16 molar, 0.82, sorry, 0.24 molar, and 0.32 molar, of course, increasing at a consistent molarity, and a 0.4 molar solution. The data is plotted below, giving us a relatively quite linear trend, which is ideal. And we're asked, okay, B, I don't really know what happened to A. What happened to A? It says, well, I guess there is no A. Oh, A was above. A, we're doing, how interesting. Where did A go? Hold on, guys. I feel like we're missing something. I figured it out. I split the question that was originally an FRQ into two different questions. Sorry, let's keep going. So we have this data plot, and it says the absorbance of the unknown solution is 0.750. What is the concentration of solution? Okay, don't overthink this. This is just graph reading. So we're going to do, we get absorbance on the Y. We say it's a 0.750. So we're going to look at the graph and say, well, 0.750 would be approximately here. Oh, if I can draw a straight line. Gee willikers. Here. So it would be, okay, let's see. Did I draw that really straight? I did not draw that really straight. If you can draw more straight than me, I think you're, oh, I know, I can use a different setting. That's what I should do. I should just draw a line. There we go. There we go. So, relatively, it's approximately 0.27 or 0.26 molarity. Okay. The AP usually, when you're doing extrapolation from a graph, will usually give you a range that is acceptable, an acceptable range. So you don't have to worry about being on the money for it, you know? Okay. So Beer's law is an expression that includes three factors and that determines the amount of light that passes through a solution. Write the equation, identify these three factors. Okay, so this is even easier. They're really just asking you, this was an actual AP FRQ. They're asking you to define the mathematical relationship that we've established through Beer's law and tell us the variables. So what we have is for Beer's law is that absorbance equals molar absorptivity, okay, times the length of the path cell times the concentration of the sample. So A equals absorbance. Epsilon equals molar absorptivity. Absorptivity. And by the way, it's unique to each sample, right? It's unique to each element or sample. I'm going to put this, unique to each chemical. I'm going to put it that way. Chemical species. And then we have length, which is length of the path cell. And then we have C, which is concentration, which is usually what we're solving for, right? We're given absorbance from the instrument, and we usually, almost always the path cell length is usually 1 centimeters because it's just kind of the standard way that we make the cuvettes. And then absorptivity you'd get from a table. And usually we're just always trying to solve for C. Okay. Okay. How about D? Or technically, I guess C, because I split the question. The student handles the cuvette and leaves fingerprints in the path of the light beam. How will this affect the calculated concentration? So remember, if you have fingerprints in the path of light beam, you're going to increase, okay, fingerprint oils, finger oils will increase or will increase the absorbance red. Okay, we'll increase the absorbance value red, and therefore, okay, will create an will result in an overestimated concentration. And I'm running out of room. Oops. Overestimated concentration determined. So Beer's law problems on the AP, remember in the notes how I went through a ton of like sources of error, what can and cannot affect it? This is a common part of an FRQ or MCQ, kind of lab-based question. Yeah, it's just an instrument that the AP tends to focus on. So why is this method of determining the concentration of nickel sulfate solution appropriate, whereas using the same method for measuring the concentration of sodium solution not be appropriate, or sodium chloride solution not be appropriate? So remember that you often have a hue. Like the idea of Beer's law is you're working with gradual dilutions and measuring based off of color absorption, essentially, or the intensity of absorption of light passing. You're measuring and creating a trend line to predict and identify the concentration value. So here's the problem. Nickel 1 is a transition metal. Well, this isn't the problem. Here's the situation. Nickel is a transition metal, and nickel being a transition metal has some type of color that is usually identifiable. But we know from our experience, salt is colorless. So given that the instrument relies on the intensity of color to represent the intensity of concentration or the amount of concentration, having a clear solution doesn't actually work with the instrument. It like the instrument just can't do anything with that sample. So how can I phrase this? So given, oops, let me write this. Given that spectrophotometry oof, my handwriting is getting real bad. Spectrophotometry relies on color absorbance and transmittance. Okay, on color absorbance slash transmittance, the colorless nature of NaCl would not be able to produce measurable results. Would not be able to produce measurable results. Okay, so I realize that kind of cut into question 37 space, but hopefully you guys write a little smaller than me. So there's kind of your walkthrough that ended up being like an AP because I ended up splitting up an AP question or actually my TAs did. And I thought that was a really good move actually. So let's go ahead now and move on to the official AP question, which is question, I believe, number 5 all the way down. And it is another, question 4, it is Beer's law. So I think actually some of you guys might have encountered a similar question on a previous problem. So here we have the student is given a sample of copper sulfate that contains a solid impurity that is soluble and colorless. The student wants to determine the amount of copper sulfate in the sample and decides to use it spectrophotometer. First, the student prepares a calibration graph, which is necessary, right? A set amount of dilutions, consistently spaced out dilutions, and measures the absorbance of each in order to determine this linear trend. The graph is shown below. And the student dissolves the entire impure sample. So key word here you might want to notice is the word impure sample of CuSO4 in enough distilled water to make 100 milliliters of the solution. Then the student measures the absorbance of the solution and observes that it is 0.30. Determine the concentration of CuSO4 aqueous in the solution. So here's one thing that you need to realize is with an impure sample, only the pure CuSO4 will make a reading. Okay, will give us a reading. So when we look at the absorbance, whatever molarity is associated with that absorbance is our pure amount. So what we have is we have 0.3. So I'm going to put it right here, draw a line. And what we'd see is it's about 0.15 molar. Okay, 0.15 molar, and that's it. Like that's the end of the question for part A. A lot of times you guys try to start doing math immediately, and it's not really necessary because what they're asking you is simply just the concentration. Then we're asked now to do math. Calculate the number of moles of CuSO4 that were in the impure sample. So we would take the value of the pure. This would be assumed pure CuSO4. Okay, and we determine the mole value. And so what we need to recognize is that in a 0.15 moles per liter molarity sample, we had 100 milliliters of solution. So what we're going to do is we have 100 milliliters of solution. So we're going to convert 100 milliliters to liters, and that becomes 0.100 in order to keep sig figs, times 0.100 liters to give us moles. And we would get that our moles of CuSO4 is equal to 0.015 moles. And for some reason, I feel like this question is a repeat from another quiz or problem, but oh well. C, in addition to the number of moles of CuSO4, calculate in part B what other quantity must be measured in order to calculate the mass percentage of CuSO4 in the impure sample. Oh, this was definitely a test question in another unit because you technically didn't need to understand all of this to do the math. Okay, so for those of you that got, I believe it was one of the versions in Unit 1 test, FRQ, and you have this problem, here's a walkthrough of it now from Unit 3 that offers you a little bit more background on exactly the concept behind the math or the concept behind the experiment where you were applying the math that you learned in Unit 1. So in addition to the number of moles of CuSO4 calculated, what other quantity must be measured in order to calculate mass percentage of the impure sample versus pure? So remember, mass percentage is going to be pure over impure in grams. So we know the mole value. So if you know the moles for the pure, you can go to grams simply, easily. But we don't know the mole value for the impure. So what we would need is we would need the mass of the impure sample. Okay. And let's see, D, draw a particulate drawing of a single Cu2 plus ion is shown below. Draw how the two water molecules would be oriented around the Cu2 plus ion. So remember with particulate diagrams, nothing is a mistake. So what you would show is that when it comes to ion dipole, this would be an ion dipole attraction, right? That unique kind of IMF/intramolecular bond. It's very special to ionic compounds. What we would have is that our water molecule would be oriented so that the more negative region would be closer to the cation, and the more positive region of the H's would be further away. So we're going to take our little Mickey Mouse and we're going to draw a little circle. And let's see my skills. Okay, we're going to do that and we're going to orient it so that we have a couple, and I'm going to turn it. How do I turn? Oh, there you go. And we'll do two so that they're closer. And that's all it's asking for. So I'll put a note in the description box that I actually think a lot of the real value would have been the Beer's Law conceptual. And for those of you, again, sorry, there are students. For those of you again that had the FRQ in Unit 1, where you had this problem and you were like, oh, I got really tripped up on the math. Well, here it is again, a full explanation now from the perspective of Unit 3, where you actually understand the process it's talking about versus just focusing on the math. So, good work, you guys, and good luck.